Hello everyone and welcome to ROS2 tutorials. In this tutorial we explain how to model, simulate and control a differential drive robot in ROS2 and Gazebo. Over here you can see a real-time ROS2 and Gazebo simulation of a differential drive robot. I can control this robot by pressing the keyboard keys. For example, if I press K, the robot will stop. If I press L, the robot will rotate in one direction. If I press K again, the robot will stop. If I press J, the robot will rotate in another direction. On the other hand, if I press I, the robot will move forward. If I press backward, it will move backward, and it can rotate if I press, for example, O. The differential drive robot consists of the body represented by this red box over here. Then it consists of two actively controlled wheels represented by these yellow cylinders over here. And in addition, we have a third passive wheel, which is basically a caster wheel, represented by this sphere over here. That is, this blue sphere is a caster wheel. That's a passive wheel and only provides the support for the robot. In this tutorial, you will learn how to model, simulate and control this differential drive robot from scratch in ROS2 and Gazebo. That is, you will learn how to write the following files. You will learn how to write robot.xacro file that completely describes the robot geometry. Then, you will learn how to write a Gazebo file that specifies controllers, additional Gazebo properties, and some other parameters. And finally, you will learn how to write a ROS2 launch file that connects all the pieces together and that executes the simulation. In addition, we wrote a detailed manual that you can see over here that explains how to model and simulate this robot in ROS2 and Gazebo. Links to all the files will be provided in the description below this video and in the comment section. Before we start with the explanation, we have to mention several important things. First of all, let's start with the copyright notice. This document, developed codes, and the lesson video should not be copied, redistributed, or publicly posted on public or private websites or social media platforms. The developed codes, this manual, and video are the property of the author. The author is Aleksandar Haber. Without author's permission, the code should not be included in academic works, student report, and student papers or theses. Also, the developed codes should not be used in a commercial setting without paying appropriate fee and without the permission of the author. Then, in this video tutorial, we provide a step-by-step tutorial on how to model, simulate, and control a differential drive robot in ROS2 and Gazebo. You have to strictly follow all the steps and we will explain all the codes. If you miss some of the steps, you will not be able to successfully simulate the robot. This video requires time and it is more than 1 hour long. Consequently, you have to reserve time to watch it and to simulate the robot. Try to understand every step that we are performing and do not simply type the code without understanding what we are actually doing. Okay. The first step is to verify that we have the correct versions of Linux and ROS2. Namely, this tutorial is developed under the assumption that you have ROS2 Humble and Ubuntu 22.04. Consequently, before even watching this tutorial, you have to make sure that you have proper versions of ROS2 and Linux. If you don't have these versions, then you need to install these specific versions. Let's start. First of all, open a terminal. Then, over here, I will resize this terminal such that you see what I'm typing and such that you can see also the manual over here for additional explanations. Okay, so to verify the Linux distribution, you need to execute this command in the terminal. Here it is. And you should see 22.04. This is very important. And this means that you have the correct Linux distribution. Now let's verify ROS distribution. To verify the ROS distribution, we simply need to do this. First of all, we need to try to source the environment, and notice here that I'm sourcing Humble, which is basically Humble Huxbill ROS2, and after that let's print the current ROS version. And I do it like this, and as the result you should see Humble. This means that you have Humble ROS2 version. This tutorial will not work on other ROS2 versions. However, it can still work if you know how to modify. However, I don't suggest you that you modify it by yourself. Try to install this correct version of Linux and try to install Humble. On my video, on my YouTube channel, you can find tutorials that explains how to install Linux and how to install ROS Humble. Also, the suggestion is not to use Windows Virtual Machine. That is, run Humble on a native Linux distribution. Okay, the next step is to install necessary packages. First of all, let's open a new terminal. And let me give you one very important comment. Whenever you want to do something in ROS, you need to source the environment. Sourcing the environment meaning that you are actually executing this file. It's a setup.bash file that sets up the environment, and this is very important. Next, we need to make sure that we have all the necessary packages. To do that, first of all, you need to run sudo apt-get update, enter your password, and after that you need to run sudo apt-get upgrade. Okay, you can see that nothing is upgraded in my case. This is simply because I run these two commands very often. However, in your case, you will probably see something is happening over here. You will see the download progress, the installation progress. So wait until these steps are completed. Then after this, it's very important to restart the computer. That is, again, after you run these two commands, restart the computer, then open a new terminal and again follow my tutorial. So what I will do, I will not restart the computer since nothing is changed over here. However, I will assume that you restarted the computer, and after restarting the computer, start from here. That is, open a new terminal and let's start again. If you don't restart the computer after these two commands, you will not be able to run Gazebo, or you might have some issues. So it's very important to do that. Under the assumption that you restarted the computer, we will continue with installing additional packages. Again, the step is to source the environment. Then let's install gedit. Gedit is a very powerful and simple to use editor in Linux. Enter your password. As you can see already over here, everything is installed in my case. However, in your case, you will see the installation progress. Then you need to install this ROS package. Then you need to install this ROS package. Then you need to install this ROS package. In the interest of the brevity of this video tutorial, I don't have time to explain all these packages. The best strategy is to Google these packages and to learn more about them. Then I need to make sure that I have Gazebo on my computer, and first of all I need to run this command to get the correct version of Gazebo. Apparently I have it since I ran it several times in the past. Then I need to install additional packages. Then I need to install this thing. Okay, now let's continue. I need to install this package, geometry. Then I need to install this package, messages. Then I need to install plugins. Then I need to install this very important package that's making a bridge between ROS2 and Gazebo. Then I need to install this package called ROS2 Teleop Twist Keyboard. This package will be used, oops, I made an error here. This package will be used to control the robot by using the keyboard keys. Okay, now we have all the packages. Next, in order to check the Gazebo installation, we need to run Gazebo. We simply run the Gazebo by typing Gazebo in the terminal, and let's see what will happen. If everything is installed properly, you will see this empty Gazebo world, and you can try to use mouse keys to rotate it. This means that we have properly installed Gazebo. Now, here is one very important comment. But before I say it, let me close Gazebo. First time you install Gazebo, it might happen that after running Gazebo, you might see some errors, and Gazebo will not start. This means that you need to restart the computer. Okay, after restarting the computer, and I will assume that you did that, you will need to again to source the environment before continuing with this tutorial. Another thing that you can verify is the current Gazebo version. You can do it like this. In my case, you can see that the version is 11.10.2, and this is the newest version of Gazebo. Okay, now, again, if you see some problems starting Gazebo, restart the computer and follow the tutorial. The next step is to create the workspace and packages. So again, to practice sourcing the environment, I will close this window, then I will open a new terminal window, I will resize it, and I will continue. Okay. Whenever you want to do something in ROS2, you first need to create two folders. These two folders are the so-called Workspace folder, and inside of that folder there will be a source folder. But before you do that, you need to source the environment. You do it like this. Sourcing the environment again means that you're executing this setup file that will set up the ROS system. To create the Workspace folder, we need to execute this command. This command called mkdir will create a folder whose name is ws_dd_mobile, and inside of that folder it will create another folder called source. This is a very important step. What is this tilde? The tilde is actually a path to the home folder. This is a standard symbol for the home folder in Linux. Okay, let us see our new folder, where it is. Well, if I do this, ls-la, and if you are in the home folder, you should actually see the newly created folder. So let's try to locate it over here. It is ws, starts with ws. Let's see, here it is. It's created on June 30. That is today. Okay, so let's again analyze what is this ws. ws stands for Workspace, and DD Mobile is the name. You can change this folder name as you wish. However, if you're a new ROS2 user, or if you're just learning ROS2, don't play and don't change the names. That is, use my names. In the later iteration, when you become more proficient, you can change the names. Again, source is the source folder. Now let's navigate to the new folder. We navigate to the new folder like this. And you can see over here that we are currently in the new Workspace folder. To see your current location, you can type pwd and you can see that you're in the home folder, username, and the Workspace folder. Whenever you want to do something in ROS, you need to do build. This will build the initial workspace and it will create additional folders. Let's see the new folders. Aha, now we have build, install, log, and source. So we created 3 additional folders and probably some files inside of them. So let's create our package. To create the package, you always need to go to the source folder. Then in the source folder, you need to execute this command. Let's analyze this command. ROS2 package create is one command. And this is the build type. M and CMake, meaning that we are going to use CMake. And this is the main thing. This is the name of the package. I will call the package mobile DD robot. So let's do that. Okay, good. Next, inside of the source folder, if you type ls-la, you will see our package folder. Consequently, let's navigate to that folder by executing this command. Okay, inside of this folder, we will create 2 subfolders. We will create the launch and the model folder. That is, make directory, launch and model. Okay, let us explain these 2 folders. The launch folder will contain the Python launch file necessary to run the model in Gazebo. The model folder will contain the Xacro and URDF source file of the model. Note that URDF stands for the Unified Robotics Description Format. This is a file format that is used to specify the geometry of robots and some other properties. Xacro is actually an XML macro language used to parameterize and simplify URDF model development. Let us now build the complete workspace once more. To build the workspace and packages, you need to navigate to the source folder of the workspace. Again, we need to go here to the source folder of our package, or actually not the source folder of the package, just the workspace folder of the package, and we need to run colcon build. And here it is. Perfect. In step number 4, we need to create the URDF and Gazebo files. But before we do that, let us analyze the sketch of a differential drive robot. Here it is. The differential drive robot consists of the robot body, represented by this black rectangle, and note that this is a top view of the robot. Then it consists of 2 wheels, this wheel and this wheel. We assume that there are motors spinning these wheels. And in addition, we have an additional caster wheel that's projected here as a simple circle, and it is from below. Our first step will be to create the main robot.xacro file defining the robot geometry and some parameters. For that purpose, let's navigate to this folder, that is to the model folder, and inside of this folder, let's create the file called robot.xacro. Okay, here in the interest of brevity, I will simply copy and paste the content of the file, and I will explain this file step by step. This is our robot.xacro file. I will save it, and I will explain it line by line. Here, it's very important that you accurately type this file. This is essential. If you miss something over here, your model will not be able to be displayed. So be careful and spend some time trying to understand what is written over here. I opened the file using another editor. This is mainly because Gedit is not the best for explaining the files. It's okay for typing the files, however for explaining the files it's not good, since sometimes the new lines are not properly displayed on the screen. Consequently, I opened the file from the Spider editor. You don't need to do that. Just type the file in Gedit or by using some other editor. Okay, so here's my robot.xacro file. Every robot.xacro file or Xacro file or URDF file has to start with this line. So this is a standard line. We write comments like this. We start the comment and we end the comment, and you can see the description of this file. My suggestion is always to comment everything. Then we have the robot environment or the robot tag. this is what every Xacro file has to have. So we start the robot tag or the robot environment. We specify the name of the robot, differential drive robot, and this is the standard part over here. Now, when you open anything, such as an environment or a tag, you need to end it. So the end is actually at the end of this file. So I close robot. Okay, let's continue. The first thing that we need to define are the body dimensions. So let's go back to our Word file, that is to our graph, and let's see what are the body dimensions. The coordinate system is oriented like this. Our body, which is called body link in URDF file, has the x length of 1. Okay, so let's see it in the file. Here's how we define. We use this macro called Xacro property. We specify the name. This will be the name and the value will be 1. Then later on in the code, instead of using 1, we will simply use this parameter body link x dimension. Again, over here we are actually defining parameters of the model. This is a very good practice to parameterize complete geometry. And then later on, when you need to refer it in the code, you will simply use body link x dimension and the code will automatically know that it's 1. It's a very bad practice to enter directly the numerical values in the code. Always use parameters, since you can easily change the geometry by just changing these first 20 lines of code. Okay, so this is the x dimension length. You can see it over here. Then we also have y dimension length. Here it is. And we have body link z dimension. You cannot see this dimension on this graph since it points out of the screen. Okay, now let's specify wheel dimensions and location. First of all, here's the wheel. The diameter of the wheel is 0.3, which means that the radius is 0.15. The wheel link length is 0.1. Here it is. And over here we need an additional parameter, and that's the wheel link z location. The center of the wheel is located at z equals to minus 0.1. That is, this point is in the negative z direction and the distance is 0.1. Next, we need to specify the caster sphere dimensions and location. The radius of the caster link or the caster sphere is 0.15. And the caster link z location is minus 0.1. Let's continue. Next, we need to define the parameters specifying density, mass, etc. Here are the densities. Here's the body density, wheel density, and the caster density. Next, we define the pi constant. This is the standard pi constant. And over here, we define the robot mass, wheel mass, and the caster mass. So what do we do over here? Here's the body mass. How do we compute the body mass? We simply multiply the density by the volume. So over here, you can see the nice property of Xacro files. You can actually directly enter the formula. So this is the formula for the body mass. So it's the density times the body link x, body link y, and body link z. That's the volume. Multiplying density gives you the mass. We do the same thing for the wheel, and here's the formula, wheel density, pi constant, and you can see the formula, and we do the same thing for the sphere. The caster is a sphere, its mass is density times its volume, and here's the volume of the sphere. That's how we do it, and this is a disciplined way of writing the URDF file. Next, we need to specify the moments of inertia of the wheel. This is the moment inertia in the z direction, in the local z direction of the coordinate system attached to the wheel. We will later on define this coordinate system. Again, these are the inertia properties associated with the wheel. So this is a standard inertia for the cylinder in the z direction, and these are actually the moments of inertia for the direction perpendicular to the vertical direction. And you can see the formulas over here. These are the standard formulas. Next, we need to define the moments of inertia of the caster sphere. I call it like this, and here's the value. Now, besides defining these inertias, we need to define the complete inertia for the wheel and for the caster. So we open this environment and we close this environment and we specify a complete code inside. When specifying inertia in URDF, you actually need to specify the inertia tensor. And this is what we are doing here. We are actually specifying the inertia tensor. Here, I wheel is actually defined over here. And this is very important. And IZ wheel is actually defined over here. So we are using later on these formulas over here. We start the inertia, we specify the origin, we specify the mass, etc. And finally we specify the inertia element and we close inertia. We do the same thing for the caster wheel. We use this and call this parameter as inertia caster. We specify inertia, close inertia, specify the origin, mass value, and inertia tensor. This is very important. These two macros called inertia wheel and inertia caster will be used later on in the code, and we define them here. This is a very good practice. Why is that? Well, we will need to use twice this segment or this piece of code, and instead of copying and pasting it 2 times, we will simply define it as a parameter, and with one line of code we can include it later on in our code. This is very important. Okay, here we need to include an additional file that defines extra gazebo options and motion control driver. We do it like this. Xacro include name of the file name. Here we use this command to find mobile DD robot. This is the mobile DD robot folder. Inside of the model, we will define this file, robot.gazebo. This file is still not defined. This will be our next step. However, we need to include it in this file. From here, we define links and joints. But before we start with the explanation of links and joints, let's go back to our graph. In URDF, segments of robot are modeled as links. So over here we have actually 1 link, 2nd link, 3rd link, and 4th link. The first link is the body link, and it's called like this. Then we have wheel 1 link, here it is, and wheel 2 link, here it is. The body is a link and the wheels are links. And in addition, we have the caster link over here. Links are connected with each other by using joints. Over here, we will have wheel 1 joint connecting the wheel 1 link and body link. And this joint will be able to rotate. Then we have wheel 2 link connecting, actually wheel 2 joint, here it is, and it will connect wheel 2 link with the body link, and we will have caster joint connecting caster link with the body link. However, the caster joint will be fixed. So let's go back to the code and let's define. First of all, in order to properly display our model in Gazebo, we need to define the so-called dummy link. This is just a ghost link called dummy, and here it is. We start the link, we end the link, we name the link. And then we need to specify the joint name. With every link we have an associated joint. Over here I will call it dummy joint, it will be fixed, and we need to specify the parent link and the child link. This is a standard practice when defining links. You always, joints actually. To repeat, this is a standard practice when defining joints. When defining a joint, you first need to define the parent joint and the child. Actually, again, I will correct myself. When defining joints, you need to define the parent link and the child link. So this is the correct statement. In our case, the parent link is the dummy link, and the child link is the body link. Okay, I will explain this later on in the code. Next, we need to define the body link of the robot and additional joints. We start the link name is body link, and over here we end the link. Over here we define the body link. We need to specify the visual representation of this link. We start visual, we end visual, we specify geometry, we end geometry. The geometry is a box. Its size is body X dimension, body link Y dimension, and body link Z dimension. We close the geometry and we specify the origin location. The origin location will not be shifted and rotated with respect to its parent, with respect to its joint coordinate system. So RPY is roll pitch yaw. These are the rotations of the coordinate system with respect to the joint coordinate system, and this is the translation. We don't have any rotation and translation. Next, we need to define the collision. The collision is used by Gazebo to detect collision between objects. We simply copy and paste this segment over here in collision. And here's the main part. Over here, we define the inertia. We need to define the inertia of our box. And here's how we do it. We specify the mass and we specify over here. Let me zoom out so you can see everything. Maybe you will not be able to see everything. I will simply move this toolbar to the right. So this is the inertia. We need to specify the tensor of inertia. These are actually the standard values that people use for the tensor of inertia of a box. You can see the formula over here. You can type. Here's this part over here. Then here's this part over here. Then you have EYY, this part over here. And in the next row, you have this part over here. And you close inertia block. And that's it. This was the body link of the robot. Next, we need to define the back right wheel of the robot and the joint. That is, we need to define this link and this link as well as their joints. Let's start with the back right wheel. Here is the name of the joint. The joint name is wheel 1 joint. The type is continuous. Continuous means that we allow for continuous rotation of our wheel. What is the parent link? Okay, so let's look at the graph. The parent link of this joint is the body link, and the child link is wheel 1 link. And this is what precisely is written. Body link and wheel 1 link. Next, we need to specify the orientation and position of the joint coordinate system with respect to the previous joint coordinate system. So we have the displacement over here. Consequently, we have translation of the origins. The translation is performed with respect to this fixed frame that I call first frame. So what is the translation? In the x direction, it's minus 0.3. Minus 0.3 is actually 2 times wheel radius with the minus sign. Then we have translation in the y direction for minus 0.35. That's basically minus body link y dimension divided by 2 minus wheel link length divided by 2. And we have translation in the z direction, since this coordinate system is located below this coordinate system, for the distance of wheel link z location that's previously defined. And over here we have RPY, roll, pitch, and yaw are equal to 0. This is very important, and we need to specify the rotation axis. The rotation axis will be actually y-axis. That is, this will rotate around the y-axis. Consequently, we have here 0, 1, 0. This is very important. Next, we need to specify the limit effort, the allowable velocity, dynamic stamping, and friction, and we end joint. Okay, again, here is the joint definition. Now we need to specify our wheel 1 link. Here it is. How do we specify? We specify visual. And over here, what I did, I rotated the coordinate system attached to the center of this link with respect to the coordinate system of wheel 1 joint. Again, what you see over here is a rotation of the coordinate system attached to the center of the wheel 1 link with respect to wheel 1 joint. And rotation is specified the radians. I only have rho for pi over 2. Here it is. And I don't have any translation. Over here I specify geometry. Geometry is a cylinder. Length of the cylinder is given over here. The radius is given over here. I add geometry and visual. Then again, the collision section is simply copy and pasted part from here. Nothing special. And notice over here the part. Over here I add the inertia wheel macro, and this macro is actually defined over here. So instead of typing this, I simply placed a single line, and that's the power of Xacro and macro. Next, we need to define the back left wheel of the robot and the corresponding joint. So let's look into the figure once more. We need to define this wheel and the corresponding joint, and the principle is actually the same. Joint name is wheel 2 joint, type is continuous. The parent link is actually the body link. The child link is wheel 2 link. Here is the origin, X displacement, Y displacement, and Z displacement. Let's look into the figure once more. For X, we have plus 0.35. Here it is. Actually, X is negative. We should be careful. X is negative minus 0.3. And here it is. That's minus 2 point wheel link radius. Y is actually positive now. It's 0.35, and that's basically body link y dimension over 2 plus wheel link length over 2, and here's the Z location. And we don't have any rotation. The axis of rotation is obviously the y-axis, and we specify it over here. Here's the limit effort, velocity, dynamics, damping, and friction. And over here we specify the link. We call the link wheel 2 link. Here's the visual representation. Again, the center, the coordinate system attached to the center of this link is rotated with respect to the coordinate system of the joint. The rotation is pi over 2. No translation. Geometry, it's a simple cylinder. Length and radius, and visual. And collision over here is simply copy and pasted from this part over here. And that's it. That was our back left wheel of the robot and the joint. Next, we need to define the caster wheel. So here's the caster wheel. Actually, you cannot clearly see it from the top view. From the bottom view, you will see it. It's a simple sphere. Again, we need to specify the joint. It's the caster joint. The type is fixed. The parent link is the body link. And the child link is the caster link, and it's fixed. This means that we are actually fixing the sphere to our body. And the sphere will actually not rotate in our simulation. However, in practice, it will rotate. However, here for simplicity, I'm trying to avoid additional complication. This sphere will simply slide over the surface in Gazebo. And here we specify the origin. That is the center of this sphere with respect to this fixed frame. We see it's 0.3 in the X. That's 2 times caster link radius. In Y direction, we don't have any displacement. This is simply because this center lies actually on the X-axis, and the Z location is the same as the Z location of the center of this joint over here. That's it. And over here we specify the caster link, we specify the visual. We don't have any translation and rotation with respect to the joint defined over here. Here's the geometry. It's a sphere. We only specify the radius for the sphere and visual. And over here the collision is simply copy and pasted from here. And notice what's happening over here. We also have the inertia. And this is the macro that's defined over here. That is, for every link, you also need to specify the inertia code block. And this is what we did for the left wheel, for the right wheel, and finally for the caster over here. And we end the link, and that's it. And we end the robot environment. Okay, and that's it. Simple as that. Notice that at the beginning of the robot.xacro file, we have actually included this file. This is the robot.gazebo file that specify additional gazebo parameters that are necessary in order to properly display this model in Gazebo. And consequently, we need to define this file. So let's do that. This is a very important step. Let us bring up our terminal and let's continue. Okay, so go back to this folder, that is to the model folder, which we used to create robot.xacro, and let's create robot.gazebo. Here it is. Okay, again, I will simply copy and paste the content of the file. Here it is, and I will save it. And I will explain it line by line. Similarly to the previous file, this file starts with this line. Here are the comments. Here I provided a link such that you can use this link to read more about the friction coefficients. And the first thing is actually to define the friction coefficients and material colors. First of all, we are defining the friction coefficients for the body link. Notice over here that I typed body link, and this is precisely the name of our body link. And this is very important. When you refer to any link from some additional file, you should use the correct name. Okay, so here are the friction coefficients, 0.2, 0.2. Here are the friction coefficients for the wheel 1 link, 0.2, 0.2, and here's the material also. Then, here are the friction coefficients for the wheel 2 link, mu1 and mu2, and material. You can also change the materials over here, colors. For example, I'm using red for the body, yellow for the wheel, and for the caster I'm using blue. And again, here are the friction coefficients for the caster link. Here they are. Notice over here that the friction coefficients for the caster link are relatively low. Okay, why I'm doing that? Well, if you put here a large friction coefficients, you will not be able to move your robot. This is because the caster is touching the ground. And if there is a huge friction between the caster link, that is our sphere, and the ground, you will not be able to move the robot. Consequently, relax or decrease these coefficients. The next step is to define the controller for the differential drive robot. We start the gazebo environment and we close the gazebo environment. And over here we are using the plugin called Differential Drive. This is the standard name, libgazebo ROS differential drive.so, so don't play with this line. This line should stay the same, and end the line over here, and the plugin. And over here we specify the properties of our controller. We are not going to play with namespaces since everything will go through the standard ROS topics. We specify how many wheel pairs we have. We only have a single wheel pair in the back. And we specify the wheel. So the left joint is wheel 2 joint. The right joint is wheel 1 joint. Over here we specify kinematics. We specify the wheel separation. It's the body link dimension plus the wheel link length. This is the wheel separation. And the wheel diameter is actually over here. And here I should actually be careful and enter 2 times. This is very important to correct, okay? Because this is a diameter, it's not a radius. This is 2 times wheel link radius. Over here we specify the limits for the torque. Let's, for example, select 5,000 for the torque limit. And the acceleration, let's for example specify the max acceleration to be 7. This is very important. And we need to specify the output. That is for publishing odometry. We want to publish the odometry, and we want to publish odometry as TF. We do that the same thing, and publish wheel TF, that is transformations and all the associated kinematic quantities, and we specify the odometry frame. The odometry frame will be odom, and the robot base frame is dummy. And this is precisely the dummy frame that we specify at the beginning of our Xacro file. We end plugin and we end Gazebo, and that's it. Okay, now you can close this file and let's continue. Let me bring up all the other things we have. Good. So we need to continue. Let's now verify that in this folder we have the two files. We have robot.gazebo and robot.xacro. Okay, the next step is to create the Python launch file. The Python launch file will be used to launch the complete simulation. And instead of running several nodes at the same time, we will simply run a single launch file that will run all the nodes. So how to create the launch file? Remember, at the beginning of this tutorial, we created a launch folder. Consequently, let's navigate to that launch folder. And as you can see over here, the launch folder is completely empty. Inside of that launch folder, we need to create another folder. The name of the folder, inside of that folder, we need to create another file, and the name of the file is gazebo model.launch. This is the correction. We are not creating folder, we are creating the file. Okay, here it is. And over here we need to type the launch file. In the interest of the brevity, I will simply copy and paste the launch file. Here it is. And I will open this file from my Spider editor, since Spider editor can better display files. So let me open that file. Then the file is located in the home folder. Here it is, source, mobile.robot, launch, and here it is. And let's explain this file line by line. Okay, so these are the standard imports. We import OS, and then we import from Ament in the Python packages, we import get package share directory. This is necessary in order to properly combine the strings for defining the directories. And then from launch, we need to import launch description. Then from launch.actions, we import include launch description. And from launch.launch description sources, we import Python launch description source. Okay, then from launch ROS actions, we import node and we import Xacro. Good. Over here, we define a function that will actually set up the launch file. First of all, we need to specify the robot Xacro name. This is the differential drive robot, and this name has to match the robot name in the corresponding Xacro file. So if you go back to the Xacro file, at the top of the file we have the name. The name is differential drive robot, and this should be the same name. Now, we need to specify the package. The name of the package is mobile.dd robot, and this should be precisely the name of the package we defined in the terminal. Now, this is a relative path to the Xacro file defining the model. Here it is. It's in the model inside of the package folder and the robot.xacro. And this is the relative path with respect to our folder defining the package. This is a relative path to the gazebo world file, empty world.world. We are not using it currently. This is the absolute path to the model. So what do? We simply use this command to combine two strings. We get package share directory, name of the package, and the model relative path. We do the same thing for the path world file, get package share directory, name package, and the world file relative path. Over here, we get the robot description from the Xacro model file. We call Xacro.process file path model file. that's defined over here, and we convert the complete file to XML, and this will be our robot description. Next, we need to specify the launch file from the Gazebo ROS package. We use Python launch description source, we join the path, we search for Gazebo ROS. This is inside of the Gazebo folder that's actually installed. We search for launch and gazebo launch.py. We are actually using this file. This is the launch description. Include launch description, then we call gazebo ROS package launch, launch arguments world, path to world file, and we do items. This will create a directory, actually dictionary, with the corresponding entries. Okay, here we create a gazebo ROS node. We called the node constructor, package is gazebo ROS, executable is spawn entity.py. This is the standard gazebo Python file for creating nodes. We specify the arguments, we specify the topic is actually robot description, and the entity is robot Xacro name. The output should be screen. Here we specify the geometry. Okay, then we specify robot state publisher, we call node. The package is robot state publisher, executable is robot state publisher, the output should be screen, and here are the parameters. And we use the simulation time true. This will actually create the robot state publisher node. Let's continue. Here we create an empty launch description object, here it is. Then we add gazebo launch, let me just do Control Z, here it is. And we add these two nodes that are previously defined, and we return the launch description object. Simple as that. Okay, I must admit that for people who are not familiar with Gazebo, this launch file might look difficult, however it's not. It's just kind of a pattern file, and you need to change a few things if you need to modify it. I created a separate video tutorial explaining how to create launch file. You should also watch that video tutorial. In the next step, we need to make some final adjustments, and finally we can run the model. Okay, first of all, we need to navigate to this folder in order to include the dependencies. Let me do it. And inside of this folder, there is a very important file called package.xml. And we need to include our dependencies over here. Okay, so how to do that? Well, let's see. Our complete model depends on the joint state publisher, robot state publisher, Gazebo ROS, Xacro, and ROS.js bridge. So we need to include these dependencies. Let's simply include them. You can put them, for example, over here. Here they are. Let's align everything that looks fine. And let's save this file. Okay, so this was the first step. Now we have all the dependencies. Then we need to adjust the cmakelist.txt file. We need to tell to ROS2 that important files are stored in the two new folders, launch and model. That is, these are the two new folders we created, and currently ROS doesn't know that there's some important files in these two folders. So let's do that. To do that, let's first navigate to this folder again, and let's edit cmakelist.txt file. Okay, so what will be the modification? The modification will be this thing. Over here, you can see this line. So above this line, add this. We are installing, or actually we are adding, two new folders, launch and model. And destination is standard. Let's close this file, and let's continue. Okay, so what's the next step? Next, we need to perform one final build of the workspace and the package. To perform the final build of the workspace and the package, let's go to the workspace folder, and inside of that workspace folder we need to run colcon build. Okay, now there are no currently errors. Then we need to source the package. That is, every time you want to run something in ROS, you need to source the package. And this is very important. Okay, we are sourcing the package. And finally, let's run the model in Gazebo. We can run the model in Gazebo by executing this command. ROS2 launch, that is, we are launching the file. The name of the package is mobile.dd robot, and the name of the file is gazebo model launch.py. Let's run this file and let's hope that everything will be fine. And let's see, voila, here is our model. Perfect. However, we cannot control this model. Let's learn how to do that. To control the robot, open a new terminal while keeping the original terminal that's used to start the Gazebo model open. Again, do not close the terminal that runs Gazebo. This is very important. In the new terminal, first of all, source ROS2. Then source the newly created package. Then, on top of that, we need to run the teleop twist keyboard. This is a very important package that enables us to read the keyboard and to send the keyboard keys and commands to our robot. So let's run this package. Okay, and let's analyze what's written over here. This node takes key presses from the keyboard and publish them as twist stamp messages. That is, we communicate by sending twist messages. You can see how to move around. Left, right, K is used to stop, and some other things. Also, you can increase, decrease the max speeds, etc. Okay, so let's use this node. I will, for the time being, go back to my Gazebo model. Then I will bring up my terminal. And if you want to control your Gazebo model, you need to keep this terminal running the teleop key twist active. That is, this node and its terminal have to be active. And then you can move the robot. For example, if I press J, I will move in one direction. If I press L, I will rotate in another direction. If I press K, I will stop. I will move forward if I press I. Stop if I press K again. U, I will rotate like this. P, I will rotate in the other side, etc. So this is how we move our robot. You can play. This is actually a computer game now. It's very interesting. And finally, let's investigate what's happening behind the scene. Here, we will learn how to obtain more information about the topics connecting nodes and messages that are being sent through nodes. This is very important for understanding the complete architecture and for being able to debug the system. So let's open a new terminal and let's source our environment. And in addition to this, let's source also the newly created package, just in case. Okay, to see the list of topics that are currently running and that are used to communicate with our mobile robot, we can execute this command. And we can see few very important topics. Command velocity is used to transfer the commands to the robot. Here the join state, here's our odometry, parameter events, performance metrics, robot description, TF and TF statics. These are the standard topics. Let's see what's being communicated through the odometry topic. I can do it like this, and I can see clearly here something is happening. I will press Ctrl+C to stop here so I can see what's happening. Okay, so let's go from the beginning. Okay, we can see header, stamp, current seconds, nanoseconds, frame ID, child frame ID. We can see pose, we can see the position, we can see orientation, and notice that the orientation is expressed as a quaternion. We can see covariances for the positions. We can see twist, linear twist, angular twist, and covariances. This is very important. Let's see what is the command velocity. What is being communicated through command velocity? Okay, we can see only one publisher and only one subscription count. And that's it. Of course, you can use some other commands over here to explore the topics and the nodes, etc. Okay, that's all for today. Thanks for watching.